Hi everyone, I'm Thusitha Dayaratne, a postdoctoral researcher at Monash University in Australia. I will be presenting our paper titled False Data Injection Attack Detection for Secure Distributed Demand Response in Smart Grids. This was a part of my PhD project, which was supervised by Dr. Mahsa Salehi, Associate Professor Carsten Rudolph, and Professor Ariel Liebman. The presentation outline is this. First, I will give a brief introduction about the smart grid concept, and then the context of system model and the attack model. Then I will be talking about our methodology mainly, and then the experiment that we use to evaluate our methodology and its results. And finally, I'll conclude the presentation with a small discussion. Now, we are in an era where our traditional power grids are gradually transforming into a much smarter grid. We had a clear distinction between different components in the traditional power grid, where we can easily identify which part to the generation, which part to the transmission, and the distribution, so on and so forth. However, with the introduction of smart grid concept, components are having overlapping functionalities, where a one component can be a distributed node as well as a generation node. More importantly, the concept called advanced metering infrastructure, which is the core capability that enables the smart grid concept, enable bidirectional power flows as well as information flows between different components that were not allowed or did not exist in the traditional power grid. With the use of this advanced metering infrastructure, people are suggesting to implement complementing technologies such as demand response system, virtual power plant, and different pricing schemes such as real-time pricing, day-ahead pricing, so on and so forth, in order to enhance the efficiency and effectiveness of a smart grid. In particular, this work, we are mainly focusing on a residential distributed demand response system where a utility company and set of households try to collaboratively minimize their total cost with the use of device scheduling or automated device scheduling based on day-ahead price signal. In this work, we assume there's a distributed demand response system where an aggregator is the one component that decides the price signal, and it sends the price signal to all the households that are connected. Manually changing the device scheduling or the device starting times is impractical given that the price signal changes throughout the day. Therefore, literature has suggested to use automated device scheduling using home energy management system, which we assume each house owner is comprised with, and all the devices that the household will contain is connected to the home energy management system, and the home energy management system is responsible for deciding the optimal starting time for each of those devices. Once the home energy management system decides the optimal starting time of each device, it will construct the demand forecast for that particular household and send it to the utility company or the aggregator. And then the aggregator readjust the price signal based on the community demand forecast to reduce their generation cost. So this iterative process converges to a global optimal solution, and each device will have their optimal starting time. As these distributed schemes use distributed setup, these setups are vulnerable for different types of cyber attacks. In particular, in this work, we are mainly focusing on one type of cyber attack called false data injection attack, where an inside attack or dishonest user can inject some fake information, particularly fake demand into the system in order to manipulate the outcome of the optimization algorithm or the demand response system. Some recent work has shown that an adversary can obtain up to 50% of cost reduction using this type of false data injection attack. Therefore, it is mandatory, also like it's a must to ensure that this distributed residential demand response system generates solutions which are fair for all the users as well as are more resilient for this type of false data injection attack. Therefore, we need to first identify this sort of false data injection attack before consuming the demand forecast in our optimization algorithm. Given this background and context in this work, we have done two main things. First, we evaluate the existing anomaly detection methods in the context of false data injection attack detection. And then we introduce an unsupervised and a supervised anomaly detection method to detect false data injection attack in the demand response context. For the more formally, this work tried to identify whether a given demand forecast is compromised with a false data injection attack out of a given set of demand forecasts. In order to develop our unsupervised method, we have used two commonly used techniques. The first one is the k-means clustering technique, and then the spectral residual method. So k-means clustering is a popular clustering algorithm, and spectral residual method is quite new compared to k-means clustering, which is used to mainly in the computer vision domain. However, in recent time, people have used suggest use spectral residual in anomaly detection as well. So we combine these two methods to form our unsupervised method, and then we use convolution neural network to develop our supervised anomaly detection method. So then we first introduce our unsupervised method, which is we named as CSR, which stands for cluster-based spectral residual. The high-level idea of the CSR method is depicted in this picture, as you can see. So we initialize the CSR method by forming a set of clusters which can be used to capture the normal behavior or normal consumption patterns or normal demand forecast of a connected community. Once the initialization phase is done, for each incoming demand forecast, first we try to identify the closest cluster, and then we subtract that closest cluster from the incoming forecast to get the residual forecast. And this residual forecast is sent to the spectral residual transformation, which use fast Fourier transformation and inverse Fourier transformation to obtain the saliency map. The beauty of the saliency map is it highlights the false data injection data point in the residual forecast relatively more significantly compared to a normal demand forecast. Then we use some sort of a threshold to identify whether the saliency map or the demand forecast which constructed the saliency map is compromised or not from a false data injection attack. And the pseudocode of our algorithm is shown in this picture, but I'm not going to go through in details through the algorithm. Please refer to our paper if you want to find out more information about the pseudocode and the algorithm. And then we introduce our supervised method, which is an convolutional neural network. In our convolutional neural network, we have two convolution layers. The first convolution layer have 48 filters, and the second one contains 24 filters. And then we have 90% trans and also two output layers. So this is like the high level architecture of the neural network. However, before implementing this particular architecture, we have tried out different combination of different configuration parameters. For example, we have changed the number of layers, number of filters, and the kernel size, and also like different pooling strategies like max pooling, average pooling, and so on and so forth. And also we have tried out different activation function for each layer, and also different dropout percentages in the final layer before, or like the intermediate layers, to come up with this optimal design for the convolution neural network. We did the convolution neural network implementation using TensorFlow, and for the configuration parameters, so optimal configuration, we have used the hyperband method to decide the optimal strategy. Then in order to evaluate our system, we need to use some sort of a data set, but the main issue that we faced was there was no real world data set that we can use to evaluate the algorithm or the applicability of our algorithm and existing anomaly detection method. Therefore, we have developed a synthetic dataset based on the peak and street dataset. To develop that dataset, we extract consumption like individual household devices consumption from 168 households for 3 months period from Austin, Texas. And then we change the preferred starting time of flexible devices, which we assume to be washing machine, dishwasher, so on and so forth, to construct demand forecast. And also we inject fake demand from 0.1 up to 2.5% of that particular day's demand as false data injection, and constructed a set of demand forecasts which roughly contains around 278,000 demand forecasts, and roughly 5% of that demand forecast were injected with false data like fake demand. And 2/3 of this data set is used for the initialization or training for our supervised and unsupervised method. And then the remaining 1/3 of the data set, which is roughly around 91,000 demand forecasts, were used for the testing. And that testing data set contains 4,946 attacks. And in terms of the evaluation, we have used different evaluation metrics, including accuracy, precision, recall, F1 value, and the false positive rate. Given the imbalanced nature of our data set, accuracy alone does not give a clear picture. Therefore, we have also used the other factors like precision, recall, F1, and the false positive rate. If we talk about the results, so first we show the result for our CSR method. We compare in 2 steps. First, we compare CSR performance with deep learning based unsupervised method. In terms of a deep learning based unsupervised method, as you can see, our CSR model produced the best accuracy, precision, recall, F1, and the false positive rate. As the CSR variant is like fully unsupervised version, and the CSR is just like semi-supervised version. As you can see, our model able to produce the best results among the benchmark other models. However, still the precision value is slightly over 50%, which is not a really good value given the nature of the problem. And the false positive rate is around 4%, which is again a high value comparatively. Then compared with the unsupervised models, still our CSR model, the combination of CSR and the CSR variant, able to produce the best accuracy, precision, recall, and F1 value. However, our false positive rate is the second best in this time, which is falling under Twitter anomaly detection method. And we have similar performance compared to the AUC value, or like area under curve. So we have here, we show the rock curve and the AUC value for the best perform best perform deep learning based unsupervised and the best perform traditional unsupervised method. As you can see, our CSR model able to produce an area of 0.94, whereas the autoencoder, which is a deep learning based unsupervised method, only able to produce a 0.9 area under the curve value, and the local outlier factor method only produce 0.93. Again, our CSR model able to produce a better value compared to other 2 methods. In terms of the supervised methods, as you can see, again, we do a similar comparison where we evaluate our convolution neural network with the deep learning based models as well as other supervised models. In terms of deep learning based models, some of the existing model not able to identify a single attack. Therefore, we only record the accuracy of those models. However, out of the models that were able to detect at least one attack, our model able to produce the best F1 value, also the recall and the accuracy. However, in our CNN models, false positive rate was the worst among all the models that we tested where the value was 0.26. So as you can see comparatively, where our CSR models FPR value was around 4.1 and the supervised model FPR or the false positive rate is relatively or significantly lower compared with the CSR value. So which is a really good advantage. However, this is a supervised model. Therefore, we can't directly compare the FPR value of the CSR with our convolution neural network or the supervised method. So in terms of other supervised models, still our CNN model able to produce the best accuracy and F1 value. And this time, so there were some other methods which produce lower or higher false positive rate comparatively. However, as future improvement, we would like to improve our false positive rate, so which would be comparatively other supervised methods. So in our conclusion, so residential demand response system are in their inception, but they will be largely available. They will be available in the large scale in near future. Therefore, we need to ensure that this demand response system able to produce expected results and resilience for different type of cyber attacks, given the distributed nature of these setups. So we cannot prevent these attacks. Therefore, we need to ensure we accommodate or we integrate reliable false data injection attack detection mechanism to ensure that we detect attacks before consuming the compromised data. However, with more comparatively, though the supervised models produce good results, in order to train the supervised models, there should be a proper data set, which is hard to be obtained in a real world context. Therefore, our suggestion is we should stick with unsupervised methods, but with the unsupervised method, still most unsupervised method produce higher false positive rates as well as low precision, which need to be improved in the future work. And further, like as a suggestion, we would like to provide that we can integrate these false data injection attack detection mechanism in between the optimization and the aggregator, which is suitable point for integration. So utility company does not need to worry about the preventing attack at the end devices. They can do the detection more closer to the aggregator or closer to the utility company and implement some sort of mitigation strategies to make sure that optimization algorithm or the demand response systems outcome will not be affected by this forced injection attack. That concludes my presentation, and please feel free to reach us if you have any question. Thank you very much.